Question 4 from midterm 2 asks us to find some things to do with the potential of a waveguide that looks like this. So to set up the problem, I've already drawn the diagram. Essentially, we have a U-shaped waveguide. So it's going to be in 3 directions. We have an infinite conducting plane on the top, set to potential of V equals 0 at a position A in the y-axis. It extends out to infinity in the x-axis and in the z-axis. There's a similar conducting plane set at potential of V equal to 0 in the xz plane, so it extends again out to x equals infinity and z equals infinity at a position y is equal to 0. And then we have this backside to the waveguide, which is held at some constant potential. V naught is equal to, sorry, not some constant potential, just at some potential V of 0 and y, which is given by this expression here, alpha times sine pi y over a. So again, we just have our U-shaped potential where the top and the bottom halves are at V equal to 0, and this back half in the y-axis extending to infinity in the z direction is given by this expression here, V of 0 and y is equal to alpha sine of pi y over a. Part A says that we know the general form of the solution to this from separation of variables is given by the sum over all n of, we have some constant an times e to the n pi x over a plus bn e to the negative n pi x over a multiplied by, again, some coefficient cn times sine of n pi y over a plus dn, cosine of n pi y over a. Now this is just the general solution given the separation of variables. We don't really want to go into that. How do you derive this formula in this question? This was given to us on the problem, and we essentially want to find some properties to do with this general expression given our setup that we have. So it says which coefficients an, bn, cn, or dn are 0. So we want to find which an, bn, cn, or dn equals 0. And we can do this. It's pretty straightforward, just given the setup of our problem and looking at some boundary conditions. So right away, we can see that x will go to infinity. Because our waveguide is in our xz plane, this lower bound on this side will extend out to infinity in the x direction. But we want our potential to be bounded as x goes to infinity. So that means that this term here, we have e to the n pi x over a. As x goes to infinity, this term will explode because we're going to have n pi infinity over a, which is equal to infinity. This can't happen as our potential has to be bounded and go to 0 as x goes to infinity, which means that all of our coefficients an must equal 0. We cannot have any exponential term e to the n pi x over a, because as x increases, as x goes to infinity, this term will diverge. So all of our coefficients a sub n must be equal to 0. Our b sub n do not have to be equal to 0 because we have the exponential of negative n pi over a, and there's an x term there as well. But as x goes to infinity in that case, the exponential goes to negative infinity, which means it drops down, it decays, and this term will in fact go to 0 as x goes to infinity. So our b sub n are okay, but our a sub n all have to be 0. So that's our first condition. The second condition is that when y is equal to 0, our potential v is equal to 0. So again, as x goes to infinity, v must go to 0. So our second condition is that when y is equal to 0, v must also be 0. So if we look here, we have sine of n pi over a times 0, which does in fact equal 0. So in this term of our expression, that works. But cosine of n pi over a times 0 is equal to 1, which does not equal 0, which means that when we're at our surface, y is equal to 0, then this term in the brackets here will not be 0 unless all dn are equal to 0. So that is our second condition, which means that dn is equal to 0. The cn can be anything because, sorry, they can't be anything. We're going to find restrictions on them after the fact given our boundary conditions, but the cn do not have to be 0 in this case because again, our sine term goes to 0 when y is equal to 0. However, our cosine term equals 1 when y is equal to 0, which means that our dn coefficient must all be 0. So again, to recap, we have the general expression for the solution to the potential in our Cartesian coordinates given the separation of variables. This is an equation that we didn't have to solve for in this problem. It was simply given to us. We might make another video a different day where you can actually derive this formula, but for now we're just going to use it. And we're going to decide which of these coefficients, an, bn, cn, or dn, are equal to 0. And given the setup of our problem, we have a number of boundary conditions which we can use in order to restrict these constants. The first one we're going to use is that as x goes to infinity, our potential must go to 0, which means that this exponential term here must have the coefficient an equal to 0 because the exponential will diverge as x goes to infinity. So that's the first condition, is that an must equal 0. The second condition is that when y is equal to 0, when we're in the xz plane, we have set that our potential at that point is v is equal to 0. And that's because our conducting plane of our waveform or of our waveguide will extend out in all directions in z and x, and we have grounded that plane. So at y is equal to 0, our potential must also be equal to 0. We can see that in these two terms here. When the sine of y is equal to 0, when we sub that into that sine term, we're going to have this equal to 0. So the cn term does not necessarily need to be 0. But in this case, when we have our cosine of 0, that's going to equal 1. And then in order for this term to be 0 and give our potential is equal to 0, that means that all of our coefficients dn must be 0. So that's the second condition that we have. So for part A, we have found that the an coefficients and the dn coefficients are the ones that must be 0. Finally, part B of question 4 asks us to use our boundary condition at v0 and y is equal to alpha sine of pi y over a in order to find the explicit expression for v of xy for this setup. So we have here an infinite sum over all the coefficients bn and cn, and because of our boundary condition v0 of y, this is going to give us one exact solution for this problem. Right away, I'm going to group together our bn, cn coefficients. So I'm going to call a new coefficient cn equal to bn times cn from what we had before, so that we now have the sum over all n cn e to the negative n pi x over a sine of n pi y over a. And we can do this because they're just coefficients that depend on the value of n. So every combination, every multiplication for every value of n of b times c is going to give us this new coefficient. We'll just call it cn, just because c is the general coefficient name that we like to give for these kind of problems. So now this is our general expression, which I didn't summarize at the end of part A, but this essentially is the answer to part A that we have. And we'd like to use this general expression, this potential, and find the exact solution given this boundary condition. So we can do this in two ways. I'll do it the first way kind of similar to how I did 3b and 3c in terms of matching with the boundary conditions. And then I'm going to use a second method called the Fourier trick in a little bit more explicit derivation with a little bit more math in order to show you kind of how this works and why we can do the matching on the boundaries like we do. So right away, I will simply just write this out for v0 and y. This is going to be equal to the sum over all n c sub n e to the power of 0 is just 1, so I'm going to ignore that term, and we have sine of n pi y over a. This is the form at the boundary when x is equal to 0. That's what I have here. And of course we know that this is equal to alpha sine of pi y over a. So if we expand this sum out, we're going to have c0 times sine, when n is equal to 0, this is just 0 inside, plus c1 sine of pi y over a, plus c2 sine of 2 pi y over a, etc. And again, this is still equal to alpha sine of pi y over a. But right away we know that the sine of 0 is 0, so that goes away, and the sine of 2 pi times any integer value is still going to give us 0 because any 2 pi multiple of the sine term is always going to give us 0. So we can go to higher order terms, but we don't have to in this case, because if we look in the brackets here, we only have the pi y over a term. So this comes in only when n is equal to 1. So we're going to find that this is the only coefficient of this sum that survives in order to match up and give us this term. So we have that c1 sine of pi y over a is equal to alpha sine pi y over a, and therefore c1 is equal to alpha. So now we go back to our general expression where we only have the c1 term survive, so we only have where n is equal to 1. So we sum over n, cn, e to the negative n pi x over a, sine of n pi y over a. And we only have the c1 term survive, so we have c1 e to the negative pi x over a, sine of pi y over a, pi over ay. And if we know what c1 is, then this gives us our final expression for v of xy is equal to alpha e to the negative pi x over a, sine of pi y over a. So again, similar to what we did in part B and part C of question 3 from this midterm, we initially have our general expression, we expand that out given the boundary conditions that we have. So here we substitute x is equal to 0. That gets rid of this exponential term and makes this our general expression. We know that this is what's going to be equal to on the boundary. Then we can essentially expand out this sum and match up the coefficients that we see on both sides. So in this case, we only have the pi y over a term left over, which means that in this sum, we're only going to have the term where n is equal to 1, and we have the coefficient c1. Then we can essentially match these on both sides. We get that c1 and sine of pi y over a is equal to alpha sine pi y over a, so our coefficient c1 is just equal to alpha. That's the only term that will survive in this entire sum, so we can substitute that in where the value of n is equal to 1, and we end up with our final expression for the potential on the xy plane is alpha e to the negative pi x over a times sine pi y over a. So this is the potential for this waveguide that we have in this problem. Like I said, continue watching to see the other method where I use the Fourier trick to find the same answer. So we can use Griffith's so-called Fourier trick in order to solve this problem and find our exact solution to the potential in the xy plane. And this will be a little bit more mathematically rigorous than the initial matching that we did previously. So given this is the general expression and this is the boundary condition, we can essentially set this up. So we have that v, 0, and y, once again, is the sum for all n, cn, e to the power of 0, sine of n pi y over a, and then this is equal to alpha sine pi y over a. So now the Fourier trick, as Griffith likes to call it, we can accomplish this by multiplying both sides by some sine term that's dependent on m instead of n, and then we integrate over some boundaries. So we're going to set this up so we have the integral from 0 to a of some sine of m pi y over a, where m is just some constant, some number, some integer value that we choose in order to make this sine function orthogonal to our potential, sine pi y over a, and then integrate over that dy. And our boundaries are from 0 to a because that is where our waveform was extended from. We went from y is equal to 0 to y is equal to a, it's the top boundary. And this is going to be equal to the integral from 0 to a, sine of m pi y over a, times the infinite sum cn sine of n pi y over a dy. Again, we choose this sine m pi y over a because we're going to use the fact that we have orthogonality between sine functions in order to simplify these integrals. So right away we can substitute, we can bring out this alpha, and we have 0 to a sine of m pi y over a, sine of pi y over a dy is equal to, I'm going to do a quick step which mathematicians don't really like because it's not really mathematically rigorous unless I use some sort of argument about the limits of an integral and an infinite sum, but physicists like to do the simplification, so I can pull this sum outside of that integral. And then now I'm simply left with 0 to a sine of m pi y over a sine of n pi y over a dy, where again this says that the integral of the infinite sum is the infinite sum of the integral, which I can do this and just pull the sum outside. So now these two integrals, due to the fact that sine functions are orthogonal to each other unless the values inside of the brackets are the same, so unless the coefficient, the integers m and n are the same, that's going to get rid of most of these integrals and most of the values of m and n, such that we're left with only specific values due to the orthogonality. So this integral gives us the answer of a over 2, then the Kronecker delta of m and n, where we still have the sum Cn, and then on this side we have alpha, and again we have that a over 2, and now we have the delta function of m and 1, because this coefficient in here is just 1. So right away we can cancel the a over 2 from both sides, and we have that the sum, the infinite sum over all n of c sub n with the Kronecker delta of m and n, the only term that survives from this infinite sum is where n is equal to m. That's the only term that will survive. So we're left with c sub m, and over here we have alpha, delta m, and 1. And again, the only term that survives this Kronecker delta is where m is equal to 1, so we're left with c1 is equal to alpha, which is what we found previously. So we can use this in our final expression. Vx of y is the infinite sum over all n, but we don't, of course, we only have the n is equal to 1 term, so we have c1, which is alpha, and then e to the negative pi x over a, where again n is 1, sine of pi y over a, which is what we found before. So again, to kind of walk through what we did in this problem, we used Fourier's trick, as Griffiths likes to call it, where essentially we take a sine function of some integer m times our pi y over a, which is, we take that pi y over a because that's what we're given in our general expression here. We essentially want to choose a sine function that's going to exploit that's the word I was looking for earlier, exploit the orthogonality of this sine function in our general solution for Vx of y. So we choose some integer m instead of n, because this m is going to be any integer value that we can choose as we walk through our sine functions in our, essentially our Fourier integral or our Fourier series. We integrate from 0 to a, which is the boundaries of our dy, which is the kind of where our waveguide extended in the xy, in the y-axis, and we do that on both sides. Then we can do a quick trick where we pull the infinite sum outside of the integral. We can simplify this integral on both sides, again due to the orthogonality of sine functions, where we're left with just that this integral simplifies down to a over 2, which comes to the fact that sine squared will give you 1/2, and we have this a in the denominator with the Kronecker delta function, which is 0 unless m is equal to 1, in which case this Kronecker delta is 1. Same on this side, but here we have an m and an n because those are the coefficients inside of our sine function. Again, we have this infinite sum over all n, but because our Kronecker delta limits us to the one value where m is equal to n, that simplifies us to our cm. And this Kronecker delta on this side simplifies us down to the only value where m is equal to 1. So we're left with the only coefficient remaining, which is c1 is equal to alpha. Again, this is a little more mathematically rigorous, using the Fourier trick as so called by Griffiths in order to find the same answer that we found before, which is then when we plug the c1 back into this infinite sum up top here for the general form, the only term that remains is where n is equal to 1, and we're left with alpha e to the negative pi x over a times sine pi y over a.